Hello guys, good afternoon. My name is Mohammad Sabir and today I am here with you. In this sessions we are going to start a heat exchanger. First thing is that okay, this topic comes under the course of heat transfer. In the sessions what we will cover basically we will cover the LMTD method and NTU method, like how to find the designing parameter, like how to find the like what will be the surface area of the tube, okay, and for the given conditions. And now the first before moving ahead, we will try to find the answer. We will try to find the answer, okay, like why we use a heat exchanger. Okay, basically a heat exchanger is a device which is used to transfer a heat from one media to another media. Okay, this is the basic heat transfer device. Okay, now the thing is that like how heat transfer takes place. Basically, a convection and conduction mix, both phenomena are there to transfer heat from one media to another media. Okay, and that is a now the thing is that okay, what is the basic constructions of a heat exchanger? What is the basic construction of a exchanger? And basically we have a two tube. The one is the inner tube, another is the outer tube. Like you can see in the screen, this is the basically a outer tube, and this is the inner tube. This is the inner tube, and like this is these are the separated from a metallic and composite layer composite layer. Now the thing is that this is the basic construction of a heat exchanger. Uh, the hot the hot fluid passes through a outer tube, and cold fluid passes through a inner tube, and due to the temperature difference the heat transfer takes place. And we have a two basic design. The one is the parallel flow design, another is the counter flow design, and we will cover in the next part, uh, next slide. And now the question is that okay, like how to find the net heat transfer coefficient. This is the expression of a net heat transfer. Like first we find the net resistance net resistance net heat resistance. Net heat resistance is what? R is what? This is the H naught A naught. This is this for the outer, and this is the ln R naught upon R1 upon 2 pi KL. This is for the uh, cylindrical conductance. Cylindrical conductance, and this is for the inner tube. Okay, this is the net heat transfer. This is the net heat resistance. And now the thing is that by using this, how to find the u is what? Basically u is the net heat transfer coefficient correspondence to H. Okay, this is the basically a expression of a u 1 upon R upon A. And by using this expression we can find the u. This is the net heat transfer coefficient, unit same as H. Okay, now the move ahead, and this is the basic heat exchanger flow arrangement. Basically we have a two flow arrangement. The one is the parallel flow design, another is the counter flow design. In a parallel flow design, basically a hot fluid and a cold fluid uh, flow in a same directions. And in the counter flow design, they are basically a flow opposite to each other. Okay, and in a parallel flow design, basically the delta theta effective. This is the delta theta. Like this is the like first hot fluid temperatures goes down, and the cold fluid temperature increases as fluid passes through a tube. Okay, move ahead. In case similar in case of here, like this is the H1 temperature of the inlet at a hot region, and this is the outlet temperature. Okay, the exit, and this is the inlet of a cold fluid. Okay, and this is the log wind temperature difference. What is the how to find this? This is the basic averaging. This kind of averaging method, like when we find the basically now the question is that, yeah, like when we analyze the heat transfer between hot to cold fluid, basically here a convection heat transfer takes place by averaging method. We find the effective LMTD. Okay, this is the LMTD effective delta T. Okay, because like basically I want to give us some flavor of it, like how this expressions comes. Okay, what is the basic fundamental behind it? Okay, like this is the hot fluid and this is the cold fluid. You know, basically this is a expression. This is a basically we take a partial element from here, analyze that how much heat transfer takes place through this differential element. Okay, and then we integrate through this pipe, and then by this analysis we find these expressions. Okay, this is the basic understanding behind it. Okay, like how this expression comes. Okay, the next thing is that this is the applications part. uh, this is the LMTD. Now the thing is that, okay, like how to find the, like we have a as a practitioner, we know the inlet and outlet temperature of a hot fluid and inlet and outlet temperature of the cold fluid. Okay, by using that we can find the LMTD. We can find the LMTD. Okay, and like we have to design this heat exchanger for this particular of heat transfer. This is the UALMTD. We know this, we know this, we know this, and behalf of that, we can find the surface area of the tube. This is the basically as an engineer we have to calculate. Okay, and now the another thing is that we like application of a counter and parallel heat transfer flow. The basically in a basic understanding after analyzing that the delta theta lm uh, the LMTD for the counter flow is more than the is greater than the is more than the LMTD for the parallel flow. Okay, and you can say that energy recovery is so high compared to the parallel flow design. So we have to use the parallel flow counter flow design, counter flow heat exchanger as a practitioner. Okay, now the thing is effective NTU method. NTU method is what? Basically, a NTU method. Uh, First, we define epsilon. This is the coefficient epsilon effectiveness coefficient. This is basically is what? Q actual upon Q maximum. This is Q maximum is what? This is C minimum. This is C minimum upon T H minus T called in. This is for the counter for first we always try to find the like when a heat transfer becomes maximum. The first we have to choose the we have to select the one either parallel flow or counter flow, and after analyzing that in a counter flow the heat transfer takes place a maximum. Okay, and then like what will be the condition for a maximum heat transfer takes place if if the if the exit of a hot fluid temperature becomes the equal the inlet of the cold fluid temperature, then a heat maximum heat transfer takes place. So we can find it C minimum of T in H minus T H exit. Okay, and then okay, this is the main reason behind it. Now the thing is that this is the Q actual is what epsilon C minimum T because when we use this effectiveness NT method, if the if basically when we don't know the uh, all informations about temperature, so we use this NT method. Okay, now the how to find this epsilon. Epsilon uh, is basically a design parameter. By using handbook we can find this epsilon. This is the I think this is for the counter flow. Now the NTU is what? NTU is what? NTU is the UA upon C minimum. U upon C minimum. Now thing is that the procedure is what? C maximum, C minimum upon C maximum, U upon C minimum. First find the NTU, behalf of this NTU find the epsilon, and then substitute here C minimum. This is what? Okay, this is what U. It basically kind of subjective. This is like first find the NTU, C minimum, U. Then we can easily find the E. Okay, thank you.